In this module, we want to start working with custom scripts. So actually editing short snippets of code to change what we see on the screen and how we analyze our data. Again, I have posted a pack of links into the chats, including links to scripts and links to specific places in Copernicus Browser. So first of all, what we want to take a look at is the custom script repository. So this is where we start. This is a big collection of visualization and data analysis scripts, from simple ones to very complex ones. It's part of the Sentinel Hub GitHub. We received a lot of contributions from users. I mean, mainly in the previous years, but also in the last couple of months. It's organized according to satellite platforms. So we have scripts for Sentinels, including some of the mosaics. We have scripts for Landsat and MODIS and elevation models, and for Planet and Airbus, because this collection is not specific to Copernicus data space ecosystem, but everything which uses the Sentinel Hub API. So what I want to show you first is just how a visualization script works. So let's take a very simple custom script. If we go to Sentinel-2 and we open TrueColor, this is what we see. This is what the typical page on the Sentinel Hub custom script repository is like. So it has a bit of a description of the script. It explains the bands we use and some images which are representative of the script, and possibly also some references. But the script itself is up here. So if you click Show Full Eval Script, then you see the full text. Eval script and custom script mean the same thing. If we put it into an API request, we usually call it the eval script. If we just tag it in the browser, then we often call it the custom script. So what do we have here? We have three very simple parts. The first one is the setup function. The second part is the actual calculation, and then the return. So these pieces of code are connecting the backend with the data storage to the front end, which is visualizing the data. This is 3 and 4, and the data mask. This is what we are using to create the TrueColor RGB composite, obviously. The data mask is a property of the data which gives us whether it's valid for the pixel or invalid. So every satellite image, every Sentinel image is going to have a data mask, because the atmospheric correction sometimes labels pixels as incorrect. And so this is our input, and our output is a 4-band output, where the bands are red, green, blue, and transparency. So it's also possible to create very fancy visualization scripts which have transparency embedded. But usually what we just do is we assign the data mask to transparency so that it's going to be empty if the data is bad, right? Then this is the evaluate pixel function. This is what we do for every single pixel. And the sample coming from the input is a parameter of this function. We create a constant variable, gain, and then we are multiplying band 4, band 3, and band 2 with the gain, and assigning the data mask. This is what we do in this very simple TrueColor image. Now, if you just click Copernicus Browser on this page, then you're getting a Copernicus Browser image with this kind of visualization applied. Does everybody have that? Did you find the Copernicus custom script repository? Everybody have this image of the little island in the sea? So you go to TrueColor in the repo here, and then down here there's a link to Copernicus Browser, and this is what you open. So it's the interface which we already know with the calendar and the data set, but in the layers panel we are seeing this little code window, and this is what we want to change. Right now we have this button clicked, load script from URL, and the URL that you have here is it's pointing to the custom script repository. So if you paste it back over here, then you will see the actual text of the script, right? This is a small bit of JavaScript code. This is what we have actually loaded. But going back over here, we can change it now. Different. Right? So if you just unclick load script from URL and open this up with open the window up big, then here's your script. What are the parameters we can modify here? The bands and The gain, exactly. Start by tweaking the gain, right? Let's increase it to 3. What happens? You just change the code and you click apply. Yes, it gets brighter. We are multiplying all the numbers, all the bands with a constant, so obviously it gets brighter. If you decrease it again, if you put it back to, I don't know, 2.1, yes, we can edit directly in this window. I can show you once more how we did it. So you have this, and then you can just edit right in here if you want. Fine. Or you can, with this button, you can open it up and then you have a larger window for editing with this from here. Okay, now we can start tweaking the bands. How would you change this to a near infrared false color visualization? What are the bands for that? 8, yes. What's next? Do we keep B3 or do we change it? Let's take a look. This is not what we are expecting, right? I think this should be 2. No. You can check. So if we just go back to Sentinel-2, false color infrared, it's band 8, band 4, and band 3. Okay, band 4 and band 3. It's weird.
The order of the band 8 or band 3, does it affect the input? Yeah.
Yes, the order is red, green, blue. Yes, if you change the order, it's going to change it because this is the natural sequence of the RGB output. No, 842 doesn't work as well. What we can do is we go back to the visualizations, and then we just look at the custom scripts for the near infrared false color. It says band 3, band 4, and band 8. No, the output order, look, the output order is 8, 4, 3. So let's go back again to the true color. What I've done, I've just copied the script from over here. If you just click on this copy button, then it's copying the code. And now I'm typing Control A to select everything, and I'm pasting it in. And so now I'm back to true color.
You selected the false color in parent production.
No, I didn't. I just wanted to check the order of the bands. So now if I change to 8,
I think it's here down important when the return image. We have to get the return image of A4.
That's right.
No matter we ask for it matters what we want.
This should be good now. Yes. It's not enough to change it in the input. You have to change it in the return part. Otherwise it goes crazy. And let's see. This is what we wanted, right? Yes, so this is how you change the bands that you are working with. You have to change them in the inputs part, but also the important part is if you change them in the return part. If I would exchange now band 4 for band 8 here, then now I'm assigning band 4 to the red and band 8 to the green. And so that's going to be something completely upside down, completely wrong. See, this is the different composites. Okay, coming back to the true color, we can take a look once more at the individual true color algorithms that are available here. Because this, right? I'm back in the repository. So this is the very simple true color script that we have here. It doesn't contain any kind of stretching. It just adjusts the gain. You have a bit of brightness. Then this is a different true color approach. And then this is the third one. We can open this one up as well. This is the default true color function in Copernicus Browser. So it takes band 432 on the data mask again. It's setting a lot of different parameters. So the mid-range, the gamma, the saturation, and the maximum reflectance. And then it's performing a slight contrast stretching function here. And then here at the bottom, I'm trying to find the RGB output. Yes, it's defining the sRGB as the RGB function of the input bands and the data mask. And then the rest is sort of adjustments. But this is giving a different kind of true color. Let's move on to the next script, the fire one. So the second one in the chat box. You can also find it if you go to Sentinel, Sentinel-2, and disaster management and prevention algorithms. And now this is the wildfire visualization by Pierre Marcuse. If you scroll in, you see that the images are quite clear. So the fire is actually very strongly highlighted. Most of the images are regular RGB, but wherever there's a fire, you have this very strong signal of yellow and red. So let's open up the code again. We want the code from the Copernicus browser and not the one from AO browser because they handle the cloud slightly differently. So here's our setup function, right? We are using quite a few bands here. RGB, broad infrared, narrow near infrared, the two shortwave infrareds, and the data mask. And then first, we define a function to decide whether we have a cloud. This is just a very, very simple cloud masking thing. Then we are defining the way the layers are blended together because we have a separate layer for the clouds and a separate one for the RGB. And now here we are defining a lot of constants from the threshold values for the individual decision tree parts, the cloud avoidance, for coloring the image, for the burn scars. Now we are defining some spectral indices like the Normalized Differential Water Index and the NDVI index with thresholds. Then we are further down with constants. We're defining true color. We are defining a couple of classes which we are assigning in the classification. And then in the very end, this is where the calculation is done, right? So it's an if query. If we have water based on the NDVI and NDWI threshold, then we are doing this kind of visualization. If it's an area affected by saturation, we apply some stretch. If it's a hotspot for the fire, we have these classification cases. So this is actually the output, which is red and yellow. Then we have a classification for the burn scars. And finally, we are returning the products of the visualization process with red, green, blue as Viz0, 1, 2, and the data mask. So now, again, we can go to the Copernicus browser link, and it's going to open up an image of a wildfire. See, here we are. So uncheck load script from URL, and then go to the constants and experiment with making some changes. Change the thresholds, change the saturation, change burn scars from 0 to 1, and see how the visualization is becoming different. Okay, you can experiment around a bit with the parameters just to see how this influences the wildfire visualization. Look, I changed this parameter, show burn scars. It was 0, and now I changed it to 1. And these yellow areas are the places which have been burned. So this is like a switch in code. This is the default version, show burn scars 0. And then it's not showing the burned areas, but it's showing the fires. And if I switch it over to 1, then it's showing me the burn scars. And if I reduce the burn scars threshold even further,
This is on what are you changing?
I'm coming just a moment. I'm trying to see what the result is. Yes, now it's giving me a bit less. What was your question?
It's just here. I'm saying you are changing the numbers based on the user thresholds, for example. We are going to change it there like randomly in order to have better visualization, or
Yes, for the thresholds, I was just checking what happens if I increase threshold, what happens if I decrease it. Right now, I think, for example, the burn scar detection is slightly improved compared to the original for this specific setting, because from minus 0.25, I changed it to minus 0.1.
Again, are there any rules based on which you should change things? It's just running.
It depends on the script itself. Like, since these are contributed by users, they are not quite done to a unified system. Typically, you define the variables like in the beginning, and then that gives you something that you can change. But sometimes they are just hard-coded in the code, and then you would edit them later on. I think we can move on to a next script, and I can show you another example. Oh yeah, kNDVI. So if you just go further down in the chat, or also if you go to the custom script repository Sentinel-2, and then under remote sensing indices, we have kNDVI. Let's look once more at this script because it has a bit of a different structure. The end product is not a direct RGB visualization. This is not intended to look like true color. Here we have a palette. So the input function, P4, P8, and STL. SCL is scene classification layer. You remember the land cover classification we were watching for Sentinel-2? That classification is inside every image because it's a product of the level 2 correction, of the atmospheric correction. And so we are using the data from this layer to assign a classification inside the data. Okay? Just remember that these are the input layers, band 4 and band 8, similar to NDVI, and the scene classification layer. And then we define a RAM. This is a color RAM. So what we have here, these little sets here, these boxes, are always sets of 3 numbers. 000 is black, right? 0.06, 0.33, 0.04 is somewhere on the green side, right? Because these are RGB. And the first number is the number of my parameter. So if my kNDVI is 0.01, minus 0.01, I'm assigning this color. If it's minus 0.1, I'm assigning that color. I'm defining a palette as a constant. And then I'm using the visualizer process, which is a color ramp visualizer taking this ramp, the one that I defined up here, right?
The colors being this is the international color, and we can put any color that we want.
These are RGB colors, so you can put them in as you want. If you define a color ramp like this, then you can define the colors with RGB the way you want, right? And then here, this is another palette for the clouds. Okay, let's do this the other way around. Let's take a look at the image, and then I can explain the code in a bit more detail. We go to Copernicus Browser link here again. And now, further down, you just go Copernicus Browser, and it's going to open up a browser window with a visualization done by Ulyssys. You're still Wildfire, yes? If you go back, Sentinel, we are looking at the kNDVI script now. What we have on screen here is a classification and a palette applied together, right? Because the green part, it goes from like light green to dark green. That's my kNDVI script, which is working on my vegetation pixels. And everything else, which is a cloud or water or a snow surface, is classified to white or to blue, to gray, to brown, because I'm using the classification from the Sentinel-2 scene classification layer. We can take a look at this in 2 separate bits. So if I just take a look at the scene classification map, I need to actually add this to compare. Okay, so look what we have now. This is the scene classification map on top, and below that we have the custom script with the kNDVI. You see what I see? So everything that's green in the classification or yellow has this kNDVI visualization from light to dark green, and everything that's cloudy or snow and ice is not classified for vegetation. That's the combination we do. Does that make sense?
Where did you mean the classification?
I just used the the scene classification map. So what you're seeing right now is a compare between the scene classification map and the kNDVI custom script. Right? So now once more, this is the evaluate pixel function. And now this is where I can explain what the script actually does. First of all, we defined the kNDVI function itself. So this is the tangent hyperbolicus function of the square root of the NDVI to the square, right? This part, BO8 minus BO4, BO8 plus BO4, that's NDVI. You know that. Now we're raising it to the power of 2, and then we're taking the tangent hyperbolicus function of it. This is where we are introducing the sigmoid transfer function with this trigonometric thing, okay? And then my image values, the color things I'm going to show, are using the visualization process of the kNDVI palette here, right? Visualizer is this thing here, the kNDVI ramp with the greens. So if my kNDVI is smaller than 0.6, then I'm assigning these values, this little brownish thing. Otherwise, I'm doing the visualizer process. Now I'm defining another one. Is it a cloud? That's what I am taking from the scene classification layer. And then my final image values are put together from a decision tree, whether it's clouds. And then if it's a cloud, if it's not a cloud, then I'm assigning it the image values. Do you know this operator with the question mark and the colon? Ternary operator? Okay, it's something for basic JavaScript code. It's an if query. So the question mark represents an if, and then the first part is the answer if it's true, and the second part is the answer if it's false. So that's how this is put together. And then in the end, I'm returning the image values, the red, green, blues, concatenated with the data mask of the sample. Okay, going back to the browser. No, is the other one? Is this one? Yes. Paste the script in. And so if you move around, you can see that the snowy and the cloudy parts are masked out. And for the rest, you have this color visualization from light green to dark green. We can take a look at a different point in time. This is late summer. So if we go to early spring, we see a different picture with a lot more snow, right? The blue is snow, and the rest is the green forests. Oh yeah, and if you go back to the meeting chat, the next link here underneath kNDVI, this one, is taking you to the place where we are, just early or mid-spring, 6th of May. And then you can see the way kNDVI works for sort of agricultural areas. So again, we have the output of the cloud classification, and we have these the individual crop fields with different levels of greenness. And I am creating a compare just to show it compared to NDVI. Yeah, here we are. So this is NDVI, and this is kNDVI. So especially in sort of the low forest parts here, you're seeing more data.
And use it up all the days.
Now, the next script I want to show you is one called Agricultural Growth Stage. Again, you can copy the link, or you can just move over to Sentinel-2. Agriculture and forestry algorithms. Agricultural growth stage. So the way this script works is it's a multi-temporal script. So now our API request is not just requesting one single image, it's requesting a time series of images for 3 months. And then within those 3 months, it's calculating the maximum of the NDVI. And then the time of the maximum of this NDVI is going to give us the color of the image. Because we're not trying to create a good composite of NDVI, we are trying to separate different vegetation types from each other depending on their seasonality. So we want to find the places which are green early in the season and separate them from the ones which are green late in the season.
Could you implement this for the small area?
Well,
Purpose?
yes, the resolution limitation would be there, but it would have to work. So there's one change you have to do in the browser for this to work. Again, you can take the link from the meeting chat here, this one. We have to change the way we access the image date. So you open up oh yes, it's already this one. This is mosaic mode. So this is automatically taking all the images from the last 3 months and mosaicing them based on quality. Like this is what we get. So what are the white areas? I'll have to explain a bit from the beginning. So our point of interest is the 30th of July, end of July. And so we have the monthly maximums assigned to the red, the green, and the blue. Everything which has a maximum in July is blue. Everything which has a maximum in June is green, and everything that has a maximum in May is red, right? And if the maximums are approximately the same, then it's white. And if the NDVI is close to 0, then it's black. So now you seem to understand, because this means that the forest and the grasslands are going to be white because they have pretty continuous NDVI throughout the year. There's no real peak. The town is going to be black. And this is our little experimental farm, right? And you see all these little patches. Those are different crops with different peak NDVIs at different parts of the year. Okay? Now, what happens if you change the date? Let's change the date from July to September. You do this not in the code, but up here in the calendar window.
I'm going to ask you a question. Instead to do this with Mac, you need to learn how to use the codes, right?
Yes. Yes, we will try and show you. Yes, now we are looking at NDVI maximums in September, August, and July. July is red, August is green, September is blue. So we are still seeing these patterns for all these little patches that we have here. And we are seeing the grasslands with the nice vegetation maximum in September, which makes sense because the grass is growing until September and then it's mowed. The forests are still white. And the areas which don't have greenness, they are black. Okay. Another little index I want to show. Sentinel-2. And then snow and glaciers algorithms. NDSC visualized normal difference snow index. NDSI. So what does this script do? Again, it takes 4 bands. 3, 11 for shortwave infrared, 4 and 2. And then it creates an index, essentially difference divided by the sum index of these bands, the snow index. Then it assigns a threshold value. If it exceeds the threshold, then we get 0.81, so red, green, blue, as sort of a blue-green color. Otherwise, it's true color. You see these lines, right? 2.5 times B04, B03, B02, that's true color. That's a true color index we've seen before. And then this is just a constant value assigned to the pixel if the value of the index is above 0.42. So let's take a look at this again in the browser. Because this is a relatively simple script that should be easy to edit. Should have started with this one, in fact. Okay, snowy place in New Zealand. So what is the value that we have to tweak if we want to change the sensitivity of the index? If we want to get more snow or less snow, where is it in the code? Okay, one step back, right? RGB, normal true color visualization for everything that's not snow. For snow, we have this blue-green color, right? The blue-green color is here, 0, 0.81. The true color is here. So it's an if-else query, right? And then we are creating the snow index up here. And we are looking at the value of the snow index. So if we reduce this value to 0.35, are we going to get more snow or less snow? I think it's probably more, because we are looking at whether the value of the index is higher than those thresholds. Yes, our snow patches are slightly larger. Or if we change this, I can say 0.3 instead of 0.8. What's going to change here? I'm changing the color I am assigning to the snow. This little 3-parameter tuple here is telling me the value of the snow. Yes. And now there's another little trick in here. So this is the default output, right? With 4 bands. This is the red, green, blues palette. And I have another output called index, which has 1 band and a float 32 sample tag. What is the value of this output? It's down here, it's index. The value of it is index val. So it's the value of the snow index here. And so because I have created this index, I can also calculate a histogram here. Once more, I can create a small study area. Okay? And if I push the histogram button here, then it's telling me the distribution of my pixels with high and low snow index. This is how I can count the amount of snow inside an area. Because in this custom script, I'm not only creating the default output, I'm also creating the index output. Because the index output is the one that's used for the histogram. Right? Here's my histogram. I have a lot of very snowy pixels over here. And I have some pixels which are like sort of slightly snowy or not much. Actually, it's a negative value, so yeah, it's absolutely not snowy.
So now the less than 35, it's less than or figure that.
I would
Sorry,
expect.
I'm adding that. So
No. I'm not sure by myself either. Yes, if the snow index is bigger than 35, then it's snowed. So everything above sort of here would be snowed. And everything below that is not snow. That's how you can create a histogram of your areas with or without snow. I'm closing a couple of windows so that my browser does not die. Oh yes, Sentinel-1 custom scripts. This is a water surface visualization script. It's a very simple one. If you open it up in the custom script repo, this is what it looks like. We are using Sentinel-1. It takes the VV, so the copolarization signal of the Sentinel-1. It applies a small linear function and then a logarithm, just to smooth out the very large values. And what you get as a result, it's like this. So this is a water surface visualization. Because of that logarithmic thing, we are now very highly emphasizing the weak signal from the water surface, and we are completely dropping the signal from the land. And this very flat area, very bright area is an oil spill. And this is the pattern of the waves.
So when it comes to Sentinel-1 data, we have this electromagnetic spectrum. And then we apply the mathematical logarithmic to make it in a small wavelength, like did. And then we analyze based on the scattering of it, right?
Not exactly. What we do is we are looking at a very small band of the electromagnetic spectrum. That's where our instrument is sensitive. It's only in the C band, in the 5 centimeter wavelength band. And we are emitting signals with this wavelength. and we are measuring the intensity of the signal coming back. And we are doing this in two polarizations, copolarization and cross-polarization. And what happens is the range of the incoming values is very large. Sometimes we get a very strong signal, sometimes we get a very weak signal. And so we are applying a logarithm to bring these values closer to each other. Instead of a linear scale, we're working on a logarithmic scale to have a better interpretation of the values. This is what we do. I have a small link here. So underwater surface roughness, there's this link. This is a very stormy place at the moment. It's in the northern United Kingdom. So this is the pattern you get when there is very high water surface roughness. So the wind gusts and vortices are sort of creating this scallop pattern as it moves over the sea. So this is how you would recognize a very, very stormy sea on a Sentinel-1 water surface roughness image. You're looking at the descriptive images, yes. Nice. Not top. No.
So with this one, you can see a storm.
Yes. You can see storms. You can see the patterns of the wind across water surfaces. So, for example, islands or winds induced by topography are very characteristic. If we go to Dubrovnik, southern Croatia, and look at early autumn images, so something like late September, they have a very typical wind which is caused by the temperature difference between the land and the water, the bora, and I think we should be able to spot it. So again, you see the wind coming sort of down here, and then in the wind shadow of the islands, it has various patterns. But this is a way to follow the patterns of the waves and the currents in the sea. This is one of the things that they use Sentinel-1 for in marine applications. Wave height is something that's very important to marine traffic, and then one of the things you can do is to train it based on Sentinel-1. Our next Sentinel-1 script is Sentinel-1 pulse color visualization. We can look at it in a bit more detail now. Yeah, we're defining a couple of mathematical functions up here with the stretch and the index of this is the stretching function, finding this for a specific range, normalizing it to 1 and 0. This is enhancing the RGB. These are a couple of colors defined. And then these are small decision algorithms to find parameters corresponding to these conditions: water, oil spill, land, and city. Then here we have some thresholds. And then in the end, we have a visualization. So if we go back over to the browser again, we can play with these thresholds, and we can see if we can tweak the classification to be a bit better or a bit more sensitive to specific conditions. Yes, these are the parameters we can influence. So if I tweak this up to 28, then we had a patch of water here on top of the island, which would probably disappear. Yes, this area has changed. It's not blue anymore. Well, this was an initial overview of all the things you can do with custom scripts. I hope you are not too overwhelmed. I think the main objective was to show you that there's a really, really wide range of possibilities you can do with just this very simple block of code inside the browser, where you can look at statistics. I hope that you can experiment around with the other scripts or find some that are useful for you. Oh yeah, there's one final thing I want to show you in the repository. So if you go to Sentinel, Sentinel-2, Among the remote sensing indices here, we have a collection from the index database. And this one opens up a massive set of spectral indices.
Which one?
Let me go back. So
Remote sensing then.
it's called remote sensing indices, and then it's collection of remote sensing indices. Okay? So this one alone is a couple of hundred indices. Most of the spectral indices that you will find in literature are probably already coded here. So if you read about an interesting spectral index or an analysis tool, and you want to test it out for your study area, then you can just go here and take a look at it in the Copernicus browser, because there's quite a high chance that the formula is there and the actual script has already been defined for you.
So the reference paper.
Yes, in the database, the reference paper is often also there. Here we go. So the scripts are there. Yes, any questions at this point?
We go to this index database. If I write NDVI, you are going to receive different NDVIs. For example, NDVI with the normal NDVI, or with red EDH with the green EDH and so much. Based on what kind of criteria that in or red EDH approach
I can try and show you.
and the difference.
Yes, these are using different spectral bands of the Sentinel-2 image. So yeah, here's my image. I go back to true color. I create a small area. And this is my spectral explorer. So normal NDVI would be using this one here, so band 8, and the red. And red edge NDVI is using one of these. And green NDVI is using green instead of the red.
I mean, I'm saying what's the purpose? They are changing the wavelength. For example, the normal one is between 600 to 750. Then they using the EDH one.
Well, some of them are, if you want to look at the properties of vegetation here in the red edge, because, for example, you're interested in vegetation stress or dry vegetation, you might want to use the red edge NDVI instead of the regular NDVI. And the kNDVI, I'll have to look up the exact script, but I think it might use a green band, and then you can do it also on, which bands is this guy using? Yes, then it's using the green band instead of the red band. So that's a different, again, coming back to a vegetation spectrum. It's using this little peak instead of this valley here. And so it's again going to be more sensitive to the visual greenness of the vegetation as well as the infrared signal. There's a lot of these vegetation indices out there, and some of them are better than others. Many of them are sensitive to the same kind of noise. But I think these custom scripts would allow you to test one against the other and experiment with comparing them in the browser before actually working them into a process request or some other task. Let's see. And let me just check whether we have anything from the online participants.
Where can I see the legend for a custom script?
Most of the scripts don't have a legend. That's a problem. It's possible to create one. Hold on. Yes. Well, you can't do it in the script. You have to do it in the configuration. This is a different thing that I'm going to show you later on. You can configure the layers in your Sentinel Hub dashboard, and there you can add a legend. So it looks like this, right? With the position and the color. And then you add it to the layer in the configuration, but that can't be shared directly to the custom scripts. Now we are going to get our hands dirty with code. I have an assignment for you. We are going to work with the Normalized Differential Snow Index, the one here. And my question is, what happens if you change band 11 to band 12? Both of them are shortwave infrared bands. Is the index going to be more accurate or less accurate? There are two things you have to change in the code: the band from band 11 to band 12, and probably the threshold value will need some tuning as well. And what you want to do is to create a compare in the browser against some true color images to see whether the original normalized differential snow index or the modified normalized differential snow index is performing better against the visual images. So this is the code, this is the script to start with. You want to recreate this script and load it to the browser until you get it in a snowy area. You can take the example directly from the script, or you can look at a different place that you like. We would want to understand how to change the code and then whether it's performing better or worse. This little piece of code, index and 2 bands, means this. So the index is generated from the ratio of the difference and the sum. Okay, this is just I'll get right reading short. It works differences, yes? Well, the eval script has these 2 main parts: the setup function, where we define what we're going to do, and the evaluate pixel, which is the actual operation. So here we are defining the inputs and the outputs. And then in the evaluate pixel function, we're defining the operation itself. Okay, so we ended up not changing the word with the new snow index. But you guys have now experimented with custom script to the level that you have changed the input bands, you have changed the algorithm, you have changed the threshold, and you have changed the output color. These are the main things that you want to edit if you are hacking custom script. So well done, everybody got to this level of manipulating the custom script. Now we are going to look into a more complex thing for the custom script, data fusion. We're not going to write the scripts ourselves, but we are going to look into some scripts which work with 2 different sensors at the same time. In the repository, we have a separate section for data fusion over here. So this is where we keep our most amazing and complex scripts. And the one I want to show you first is, yes, the first thing under data fusion. It's Sentinel-3 land surface temperature. Now this script has a bit of history. If we go over to Landsat and Landsat 8, land surface temperature mapping. This is a script with a rather nice explanation. Essentially, what you do, hot surfaces have infrared radiation, right? So thermal remote sensing has its own special section of the electromagnetic spectrum. But the problem is that the reflected or emitted radiation from a hot surface depends on 2 things: the temperature of the surface and the material, right? And so if we are just looking at brightness temperature, we are not so close to actual temperature in Kelvin or Celsius because it's also influenced by the material. And so what you can do is you classify the surface to a certain extent to get the material, and then you apply a specific coefficient to each of the surface types, and that's how you convert to temperature. Yeah, emissivity, that's the parameter that you use. Very good. So, of course, you're not actually mapping emissivity because that would be a deep learning script or random forest, but you are using some main categories like buildings and vegetation and water. And so if you are doing this in Landsat, then you have an easy job because the images that you are using for the classification of the surface are there in Landsat, and your radiative temperature, your thermal imagery is also in the same Landsat collection. So you're just taking one band and the other band. We can take a quick look at the script. It's a complex one, but it's nicely documented, right? So what it does, minimum and maximum values for the output color, input data. It's using NDVI and in order to separate bare soil from vegetation, right? It has these 2 thresholds. Then these are the emissivity coefficients for water, soil, and vegetation. This is where you have a decision tree, right? If, else if the land surface emissivity corresponds to water, then it's water. If not, then it takes a look at the NDVI, whether it's soil or vegetation. And then further down, it applies the calculation of the temperature based on these emissivity parameters. And it's going to apply a visualization process with a color palette, right? What you have to remember from this is we are doing the classification, and then we are using that classification to feed it to our temperature estimation. Now, you can do the very same thing for Sentinel-3, but there's a difference. The problem is that Sentinel-3 imagery is in a different collection than Sentinel-3 thermal data, and so you have to create diffusion. You have to define two separate data collections, and that's where you are approaching the individual variables. So if you go to the link I provide here, again in the chat, is tinyurl1, then you will see a scene from the Hungarian heat wave in this summer. And so this is the little key that you will have to use if you want to load this script, just by copying and pasting. You say use additional data sets, OLCI, that's the spectrometer for the imaging, and SLSTR, that's the temperature measuring tool. And then this is the script, and this is the temperature map. And what you can do is you can start by changing the temperature limits. Okay, now we are between 0 and 50 degrees. If we go down to 40 and raise the bottom threshold to 15, then some patterns are going to start to emerge. You can add the rows. See, and then now you will have an impression of where the hot and the cool parts of the surroundings of Budapest were during this heat wave. So what's the hottest place? It's the airport, right? See, this is the airport. That's the whitest place, the hottest place. We can actually look at the background image for a second, right? It's the airport. This is some factory places. Also, bare soil is getting very, very hot. And we are somewhere up here. The forests are nice because they are cold. And large industrial areas and parking lots are bad because they are very hot. This is a data fusion script. I want to show you once more how to load a script like this if you don't have a direct sharing link, because it's a bit of a process. It's also described in the script itself. Yes? So now we are going to load this image, but from scratch without the sharing link. So let me check the date. We are at the 30th of July, 2024. So just a fresh browser window. We are zooming into Gödöllő or Budapest, and we are selecting Sentinel-3, right? And now our image date is the 30th of July. Okay, everybody arrives here. Just a sort of true color image of Sentinel-3 for the 30th of July 2024. So I've chosen this date because there are hardly any clouds. Clouds are always influencing thermal imagery because they are cold, right? And now we want to load this data fusion thermal script. So what we do is we go to custom. Now, what you want to do is you paste in the script, but you don't apply it yet. So you copy it with this button here, and you paste it into the browser window. Again, you select everything with the mouse or with Control A, and you paste it in, right? Apply. See, we get an error message. The dataset with the ID S3 SLSTR is not found. So what we do is we say use additional datasets. So this is our primary dataset, right? S3 OLC, this is what we loaded. And our additional dataset, we selected from the menu. And it is S3 SLSTR, right? This one. This is what we have to do in order to load that layer as well. So now that you select it, you click on the plus, and then it's added. You don't have to customize the time span because you're using the very same time span. And now, all goes well. I think you can load the script, or you can just zoom into the image. Okay, what am I doing wrong? Yes, here we are finally. Okay. So actually the correct order is first to add the additional data set and then to paste the script in. But then it works. In the documentation of the script, this particular one, there is a relatively detailed description of how to use it, right? So this, what we just did, is actually written in quite details. You select Sentinel-3 as the data source, you visualize, you choose custom script, you create the additional data set, and then you paste the code and you refresh the eval script. And then you also have the option to output average temperature or of a time period or the single temperature. Average temperature would be like here. You change this to option 1 and you add a time frame. And I hope this is going to like, okay, this is probably a network thing now because it should be querying images from a month. But this way, with the same script, it's possible to calculate the average temperature or the standard deviation of the temperature for a time period. Okay. Any questions for this one? Okay, moving on to the next script. This is going to be the most complex of all of the ones that I want to show now. It's called Sentinel-1 flooding visualization. And here we are combining Sentinel-1 and Sentinel-2. We are putting one on top of the other. So if you just copy the link, this one, flooding visualization. So what this script does is it makes a water surface classification from Sentinel-1 and it displays it on top of a background image from Sentinel-2. Why do we want to do this? Because radar images are sort of difficult to interpret. So if you want to find which areas are flooded, but everything is covered by clouds because you have a flood, then you can take a historic image from Sentinel-2 or a mosaic and overlay the radar image on top of that, the radar data on top of that. And you want to put it on a 3D image to make sure you're not making any mistakes. But this is how it works. So again, I can give you a share link. It's in the chat. I hope it's going to work. This one, Duna flood. We had a flood on the Danube. I think it was at the end of summer or early autumn this year. So this is what you see. The blue and the black areas are from Sentinel-1. The green is from Sentinel-2. And it's combined into a script which visualizes both of them. And these are the areas which are flooded, which are not normally underwater. This part, this one here, this one, this over here, these things. So that's what the flood looks like. Let's take a look at the code.
We can use this code for everywhere, right?
Yes, this is open source stuff. You can use it for anything. In the setup function, we have two data sources with bands, right? Data source S2 L2A and data source S1 grid. And from S2 L2A, we are taking the bands for actually for a near infrared false color visualization, right? We're working with band 8, band 3, and band 4, and the cloud mask. And for Sentinel-1, we are picking the VB, the VH, and the data mask. And then for the output, we're just taking one single output with 4 bands, red, green, blue with transparency. And then the first thing we do is we convert, this is how to convert a Sentinel-1 signal to decibels, right? It's just 10 times the logarithm based on the base of 10. S1 is the sample from the Sentinel-1 dataset. S2 is the sample from the Sentinel-2 dataset. We are calculating the Sentinel-1 VV in decibels and checking whether it is smaller than -15. This is our flood masking algorithm, as simple as this. So if the logarithm is below -15, then we take it as a flood. Why is that? Remember that water surfaces have very low reflectivity because of specular reflection. You can actually change this to tweak your algorithm to have more or less water. And then what we are doing here is we are creating something which is very blue, right? we are multiplying the VV by 10 for the red channel, 10 for the green channel, and 50 for the blue channel. And in transparency, we have 1. So if it is a water surface, because the intensity of the VV is below -15, then we do this colorization with blue. Otherwise, we take the scale factor of 2.5, and we return the band 8 actually in all 3 of the bands. So this is a black and white image composed of the near-infrared bands. In this version, in the Copernicus Browser version, it's a bit more clearly commented, right? This is the threshold for water detection. You reduce it for more water and you increase it for less water. Up here, right? This is the EO browser version. This is the Copernicus browser version. Okay? This one has a bit more code. This is the gain value for more image brightness. You can increase it. And then what we have here is just the near-infrared image in all 3 of the bands. So it's going to be a black and white image of the near-infrared band. And these are the 2 things that we put on top of each other. If it's a flood, we take the pixel value from Sentinel-1. Else, if it's not a flood, we take it from Sentinel-2. That's how it works. And there's also a third version of this code with a different data source, where the data source is going to be called custom. And that's the Sentinel-2 mosaic. And the way you use it then is that you load first the Sentinel-2 mosaic, and then you add the Sentinel-1 image on top. We're going to do this in a moment. Again, here's the threshold value, and here's the color thing. This is true color, yes. So in the Copernicus browser version, this is just grayscale, because in red, green, blue, we have the same band. In the mosaic version, it's band 4, band 3, and band 2, so it's normal true color. We go back to our image. Remember the parameters, it's the 1st of April, okay? Is that possible? Oh, yeah, it's the 1st of April because of the mosaic. And then it's the 19th to 25th of September. So if you want to take a look at like this, you can open up another browser window again. First, you want to load your mosaic. So you go to Sentinel-2 quarterly mosaics, and you select it from one specific time. Like, okay, but first we got that's the latest one. Our location is just north of Budapest, right? This is Budapest, and then this is the Danube Bend, just a couple of 15 kilometers to the north. Okay, my data collection is Sentinel-2 mosaics, and I'm using the mosaic from April. This is where I start. Now, I go to custom visualization, custom scripts, and I say use additional data sets again. Okay, this is the key to loading the Sentinel-1 data on top of the Sentinel-2. My primary data set is the custom data set. That's the mosaic. And my additional data set is Sentinel-1 grid, right? I give it plus. And now I say customize time span. And this is where I want to put in the date of my flood, because I'm taking the Sentinel-1 image from a different date than the mosaic in the background. So my flood was between the 19th and 25th of September. Okay, so now I have my custom time span. And this is the point where I am copying the code, the Sentinel-2 mosaic code from the custom script repo. And I am pasting it into my browser window. In Budapest, there was not much damage from the flood, but actually you see it's a bit grainy. So you might want to change the threshold value, the limit parameter, and then you might get a better discrimination of water and land in the... That's just the color of the water. No, that's from Sentinel-1. This is the parameter that you can change to make your water detection better, right? Decrease for more water, increase for less water. This is sort of the last hands-on module of the day, but before we go back to editing custom scripts, I want to show you configurations in Copernicus Data Space Ecosystem. So if you go to the front page of the data space, under Analyze Data, you have Sentinel Hub, and this is your Sentinel Hub dashboard. So this is a place where you can keep track of your processing units and your API keys and your credits usage and your account type, these kinds of things. And it also contains your usage statistics, quite intensive for me in the last couple of days. And this is the configuration utility. So here you can create a custom set of layers, which you can then push to the browser for somebody else. And then they have a selected box of information for a specific area with specific visualizations. Let me show you an example. Am I in the right place? I have too many windows. Yes. So here's the configuration tab, right? We haven't touched this yet. It's always on default, or we can go to themes and highlights. But if you define a custom configuration, then you can open it up here, or you can also share it with somebody else, so that they can take a look at it. I've defined a custom configuration called Wildfire Grease. I have this fire here, and this has only 2 layers, right? Sentinel-1C, but you don't see the regular layers, true color and near infrared and whatever. I have 2 layers. One is called Active Fire, and you won't be surprised to see that this is the PR Marcus custom scripts for fire. And the other one is called burnt area. So if I want to create a product for the, I don't know, fire department of Greece, I can make them a custom configuration. And then if they open that, and this is all they see, they don't have all the controls to get confused. They can look at these 2 variables, and they can still use the calendar panel to switch back and forth between dates. And the way you create something like this is in the configuration utility, you can add a new configuration. And then to the configuration, you can add the layer. And then for the layer, you have to select the data source. And here, you can add a custom script, right? So for the layer, you specify this layer is working based on Sentinel-2, L1C. And then in the custom script, you paste the very same script from the repository. Yes. Yes, from where? From
Where did you get the configuration?
here in the Analyze Data Sentinel Hub.
I opened the one.
Yes, it takes me to the Sentinel Hub dashboard.
Yeah.
And then here I have a configuration utility.
Oh.
This is what I'm looking at. It's not going to look the same for you because I have 20 different custom configurations. For you guys, it's probably empty. Yes. So you create a new configuration if you want. And then in this configuration, you can define new layers. And for these layers, you can set again the parameters using the custom scripts. I just wanted to quickly show you this and then go back to custom script editing. But if you're interested, then we can spend some time with this tomorrow. Shall we try and take a look? Creating a configuration. Okay. Going back to our scripts, we've done the heat wave. So now let me show you my favorite custom script. It's a water quality custom script. So you go to Sentinel, Sentinel-2, and marine and other water bodies and algorithms. And it's called the Ulyssys Water Quality Viewer. It's named after the company I used to work for back when I worked for this company. Don't click at the code yet. Okay, just scroll into the documentation. So this is what it does. It creates very simple visualizations of suspended sediment and chlorophyll in water. It's based on Sentinel-2 and Sentinel-3. It uses this palette. Does everybody have the script? So this is not, it's combining true color and water quality visualization in a specific way, which I'm going to explain soon. So the 2 main parameters of water quality are suspended sediment, which tells you, how transparent your water is. Is there any light in the water column? And chlorophyll, which is telling you the amount of algae, the amount of biological production biomass in the water for your food chain. In a very restricted way, of course. It's a lot more complex than this. And the problem is that sediment is not transparent. So if you have a lot of sediment, you don't really see how much chlorophyll you have in your water, right? And so what we did was we created this palette, where if you have a lot of sediment, you don't see how much chlorophyll you have in your water. If there's not that much sediment, then the brown layer is sort of transparent. And if we have a low sediment concentration but high chlorophyll, then it goes from blue to red. So actually, we're handling two transparent layers on top of each other. And in addition to this, we have a cloud masking, and we also have a water masking in the index or in the custom script. Now we can look into the code. You want to look at version 3. Show full about script. This is long, but what you see up here, you can select different indices for chlorophyll and suspended sediment. You can choose between 2 or 3. You can choose between different indexes for masking water from dry land. One is NDVI, that's a classic one. And the other is the Holstein cloud mask, which also creates a water mask. These are the minimum and the maximum values for the color palette. And then here you can adjust the graphics, whether you want to include the non-water areas or not, right? And then we have a setup function with all these bands and the data mask. And we are creating 4 different outputs. The default output, the index, which is the one you can use for histograms, the EO browser statistics one, which is the one you can use for time series, and then the data mask. Okay, these are the indexes we use for chlorophyll. So FLH, RLH, MCI are different calculations that you use on the bands. These are the bands we use for suspended sediment. This is the masking algorithm we use to separate water from land. And this is our true color algorithm. This is just a bit of a helper function to do the blending between the layers. And then somewhere down here, we decide whether it's water. Then we decide whether it's cloud. And then we create the image from the layers. So this is something like, I don't know, 300 lines. You've seen how sharing Copernicus Browser links works, right, with these short URLs. This is because when you are editing a script, the whole script goes into the URL, and that's the query which is passed to the server. So there's a limit of how many characters can go in, and the shorter your script is, the faster it's going to work. So we made a nasty trick here. What we did was we minified the script. Okay, can close this back. Don't. We have a little link over here for the minified script, which looks like this. So there's an automatic tool which changes all the variable names to single characters. It deletes all the comments. It deletes all the unnecessary line breaks. And then it makes your script as short as possible. This can be done automatically. So this is a very, very short version. Here you have the parameters that you can change. And then down here you have the actual script. So now we can go over to a scene. We have, it's called tinyurl.com/balatonwq for water quality. I look, it's going to load. Then what we can do is we take one of the Copernicus browser links in the custom scripts page. That should work as well. And here, ensure as we will in the speed, warmer to short and is when you will that's in the documentation of the code actually. Here in the very end, how to modify the script. Yes. You would need node.js for it. And then you can use npm run minify. That's a node.js is a coding tool for JavaScript. So if this little tiny URL thing is not working, and I suspect it might not be, then what we do is we just in the script we have here evaluate and visualize, right? This part. And then you just click on Copernicus Browser over here. You can also look at one of the other ones if you want, but I would start with this one. My fingers are crossed that this is going to work. Oh yes, here we go. Yes, now we are talking.
That is good.
So what you see here is a natural disaster. So we have, in 2019, we had an extreme situation with very high chlorophyll concentrations and algae blooms on the lake. And so you remember the palette that red was very high chlorophyll and green was sort of still quite high. And this is the pattern that you saw on the lake. Let me draw your attention to this part over here. You know what's happening here? No, this is actually so bad that the water mask is failing. We can take a look. So if you remove the Holstein water mask and only keep NDVI like this, then I think most of it is going to disappear. Yeah, most of it is gone. Some of it is still there. If I would be to completely remove the water mask, it's going to run like this at all. Yes, now you see what's going on. Like this is the worst place. You can put it back. Okay. These are the limits for the palette. So we can change these. For chlorophyll max, we can say, I don't know, 0.08. And let's see if the pattern changes a bit. Yes, it does, right? See? So now it's not so red because I changed the maximum chlorophyll. I put it up higher. So this, the masking is still wrong, but the palette is different. So with this script, you have a lot of parameters that you can change. If you go back to the documentation, these are the possible values for the chlorophyll index and the suspended sediment index, right? You can test individual indicators and see if the output is different. And you can also experiment with keeping the background in the foreground, because since we are doing a water masking, we have separated the background and the foreground. Foreground is everything that is water, background is everything else. So one thing that you can do is you can set the background to black. Like this. Or you can even change the background opacity to 0.5. And then you are sort of darkening your land areas, but you're still keeping the RGB a bit in there. So I'm giving you a couple of minutes to play around with this script. You can also look at time series or go back in time. And then I'll be here to answer your questions. You can look at it, a different area if you want, or one of the other examples in the documentation. But even take a look and try and create that very informative or very pretty image. So if you create an area of interest, you can even look at the quantitative time series. So one of these lines is going to be the suspended sediment, and the other one is going to be the chlorophyll. Let's go. So here I have a situation where my sediment signal and my chlorophyll signal is mixing, right? You see that the sort of the transparency of the brown layer is influencing the red to yellow layer of the chlorophyll, because we have concentration levels where these are sort of interacting with each other. And then if I go back in time to, I don't know, February, and I expect to have much better conditions like clear water, maybe some sediments. So now I put the Holstein cloud masking back. And so now it's nicely masking my clouds away. Hope this is working. I think I have one final challenge to break your brains before the day ends. Take a look at the Green City custom script and change it to use kNDVI instead of NDVI. Sentinel-2. Urban something. Lasker land use urban planning Green City custom script. Okay, this is a very simple visualization. What does it do? It takes NDVI, it has a vegetation threshold, it creates an RGB image, it transforms it to black and white. And so if the NDVI is larger than the vegetation threshold, then it applies this color, the green color, and otherwise it just takes it turns it to grace fade. This is what it looks like, right? Green spaces in the city are green and everything else is gray. And now I want you to open up a browser window for a city of your choice. Use this custom script, paste it in, but change it to use kNDVI instead of the regular NDVI, and then adjust the thresholds to make it look okay. Maybe even the game. Okay, creating a new script by playing Lego with parts of existing scripts. That's the last thing we are doing today. So where do we start? Let's find a city. It's difficult to find Sao Paulo actually in the browser because there's this special character with the O, and that's not so easy to paste in. Let me see if this works. I can use Google search. Hold on. And there are lots of other places called Sao Paulo in different countries.
Yeah.
Okay, this is Sao Paulo. We open a custom script window, and then we take the Green City custom script. This place is too big, it doesn't fit on a Sentinel-2 swath.
But yeah, this is the city.
Yep.
But when you get to select the state because it's both at the same,
Yeah, that's the problem.
the state and the capital.
First, I'm pasting it in just as a comment to make sure I'm getting it right. So double specially connect.
kNDVI, where was it?
It was in the
Reminds.
in the custom script repository under remote sensing indices. Sentinel-2, remote sensing indices, kNDVI. Right? And you don't need the whole script, you just need the actual part where kNDVI is described here.
We don't need the other one, we put it each one.
Yes, you place this line in. Just make sure the variables are handled the same way, because this doesn't say sample.b08, it just says b08, which is okay. So you delete the little part here that says sample. And then we can comment this out. We don't need to delete it straight away. like this. And now where is NDVI used in the code? Here, right?
Yeah.
Okay, let's see what happens. First of all, what do we have here? Okay, yeah. He doesn't have a setup function. Does he? Makes it strict? No, there's no setup function. This is just an overly simple implementation of it. That's why we're not using samples.bl8, because we're not setting it up in the beginning. We're just taking bl8 from the imagery. So this is kNDVI, as we took it from the kNDVI script. This is the threshold. And this is the parameter that we can tweak. And then this is just the regular RGB transform to black and white. And this is the implementation of the threshold and the greenness. Like red, green, blue. Okay, so that's 1.8 is making it green. If I would make this 2.0, it could get even greener. But we are separating vegetation from built-up areas based on that limitation of 0.4. And probably for kNDVI, that's not right. It works differently in that range. So you will have to see whether you need to reduce it or lower it. Do you want more vegetation or less?
It's 0.8, it looks good.
Yes.
It's perfect.
Okay, well, what have you learned today? A lot, right? Remember, we started the day with Sentinel-2 interpretation. It feels like it was 3 days ago, wasn't it? Understanding different properties of Sentinel-2 imagery. Then we moved over to Sentinel-1 a bit. We completely skipped Sentinel-3 and Sentinel-5P. So in that part of the day, we are just understanding how to look at the satellite image. And then I dragged you guys through all the different custom scripts that you can work with. And of course, there's lots more. So the impression I want you to have is if you have a remote sensing problem, there's probably already a custom script out there for it. And the other thing I hope you learned is that if there isn't, you can always make one, because it's not that difficult to change custom scripts. The nice thing is, again, that the whole satellite data management part is taken care of by the backend. The visualization is done by Copernicus Browser. And this is the exciting part, right? What's actually happening with the data. And you can tweak that with simple JavaScript codes. The challenge of the day is not very surprising. I want you to create a new custom script or to change an existing one. Thanks for bearing with me all day. I mean, this is intended, and looking forward to seeing you tomorrow.